Greetings, physics fans. Today we're talking about thermodynamics and the fundamental laws of thermodynamics. Now this is actually attempt number 2 at this video, so I already have it all written out, so I'm just going to play the slide the paper up game. So the first law of thermodynamics is basically just a law of conservation of energy. I've told you many times before that conservation of energy is probably the most important single principle in physics, and that's why you see it over and over again as the first or second law of all of these different subjects. And so we've talked about the first law before. It's just that the change in the internal energy is equal to the heat that flows in. I guess heat flow is a bad term because heat implies a flow. But the energy moving in to the system as heat plus the work being done on the system is going to be your change in internal energy. And that is just conservation of energy. So the second law is a little bit more involved. It's the law of entropy. And the second law says that for any reaction that you do, that the entropy of the system plus the entropy of the surroundings must increase for any reaction. Now, there's some theoretical reactions which don't exist in real life, but they're just purely theoretical. Like, in theory, you could do this over an infinite period of time and have no entropy increase, etc. But or I do this instantaneously and have no entropy increase or something like that. But that doesn't really exist in real life. So in practice, the entropy is always increasing, or we'll say in theory it could be 0, but it never decreases. So the universal entropy always increases. So we can also write this as the change in entropy of your system is equal to the change in the heat over the temperature. Now that's a equation that only works for constant temperature. Now if you see this written more often in the calculus version, written as TdS equals dQ. Alright, so now we're going to talk about the third law. The third law says that entropy approaches a constant value as temperature approaches absolute 0. So at that point it's just based on arrangement, I think, of the particles. So if you have it arranged and, I don't know, if I have things mixed, right? There's a higher entropy just based on having it mixed, regardless of what their energy is and what their speeds or velocity or momentum is, or spin states or anything like that. So we can write this as an equation where we can say that the entropy of the system, people usually like to write it in this first way, though I think this way is a little more clear. So your entropy is equal to Boltzmann's constants times the natural log of the number of microstates you have, which is what I've written as omega, plus some constant value for entropy for your system orientations and setups. And omega being the number of microstates. Now, a microstate, you can think of it as basically the number of ways in which something can be arranged. So maybe the best way of thinking about it is a good way of thinking about it is thinking that with dice, right? You take 2 dice. Maybe I should get 2 dice. All right, I'm back with dice. So what if I roll 2 ones? How many ways are there to roll 2 ones? Or a 2. The macrostate would be, the result would be 2, and the microstate would be that it's 2 ones. Well, there's only one way to do that because I can only roll 2 ones, right? But now, if I said I want to roll a 3, now how many ways can I do that? Well, the left dice could be a 1, and the right dice could be a 2. I guess technically it's die. Or I could, what if I did it the other way and said the left die is a 2, and the right die is a 1. That's 2 different microstates. Well, it's 2 different microstates if I can tell the difference between the die. Like if I have it with my dice from Catan, then I can definitely tell the difference. It matters which one's where and which one's which. right? Because that's the same thing basically. It's just different position. Now I could also do it where I have it like so, right? That's a different orientation. But with the white dice, so it has that. I'm going to pause it real quick. I'm going to move them around and see if you can tell which one's which. Now, did I switch the numbers on the dice or are they the same? You can't tell because in like quantum mechanics, I look at a proton's a proton, a hydrogen's a hydrogen. I can't tell the difference between two of them. So you don't know if I switch the dice or not, if I switch the sides. So you can't say that it's different based on which dice is which. Because if I said, let's switch this one to 1 and this one to 2, is that different? Right? So, yeah, this law is all the number of microstates. So if I took them and I said, what's the most entropic roll you can have? It'd be the roll with the most possible ways, or the most entropic macrostate, right? What's the most entropic number you can roll? So it'd be the roll with the most number of ways to get that, right? Most number of microstates. And so that roll is actually with 2 dice, a 7. Because I can go 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, right? So there's 6 different things I can roll to get that. And everything else is going to be lower. So the 7 is the roll with the most entropy. So one of the things I think is really cool about the law of entropy is that it is a law driven by statistics. It is not like the governing principles behind it is statistics. And it's just basically saying that if I have 10 to the 23 particles, statistics laws aren't just general rules. They are firm guidelines and firm, like it's always going to follow these, given 10 to the 23 chances, which is interesting. All right, so now if we look at the last law we're going to talk about is the 0th law. And the 0th law says if 2 systems are in thermal equilibrium with a third system, they are in thermal equilibrium with each other. And this is just a fancy way of saying, hey, let's use the transitive property of equality for temperature. Because it's like saying if I have a system where I have gas A and a container touching gas B, and gas B touches gas C, and I know the temperature of A equals the temperature of B, which is the temperature of C, then I know that the temperature of A equals C. So, yeah, I don't think this one's, personally, I don't think it's that profound. But they use it more as a definition for temperature and as affecting that. All right, hope you guys enjoyed this video. I'll see you in the next one.